Titration analysis time. Okay, so some of this hopefully is review from 123. I know it's been a while, let's brush it off. You're doing a lot of acids and bases in class, so we want to get good at these. So the first thing is calculating titration molarities. And hopefully this is going to be fast. Let me give you an overview of what we're going to do in this analysis. So the first thing, which you are doing already, hopefully you've done them and sent them in to me, the volumes of the HCl and the volumes of the NaOH that you added from the burette for each run in Part A. Remember, we did at least 3 good trials where we started with 25 milliliters, about 25 milliliters of HCl. We had an initial and a final burette reading, and then we put in the indicator, and then we moved over to the NaOH burette, and then we had an initial and a final of how much NaOH it took to get to endpoint. Well, I need to subtract those final minus initial and get the volume of HCl, hopefully around 25, and the volume of NaOH that it took to reach endpoint. So you are going to report that. So that's 6 numbers, 3 titrations, and an HCl and an NaOH for each one. From that, we can calculate molarity. We'll talk about the details, but so you're going to calculate the molarity. Now first, you're just going to calculate the molarity of your 3 runs. So you get the concentration of NaOH for each of those 3 trials. Maybe you did 4. And from that, then you can get an average. So we're going to use that average in the next part. You're also going to need to get some statistical things like standard deviation, percent, relative standard deviation, and part per thousand error. And so we'll talk about how to do those. So you basically do the titration formula, get a molarity, average, get some statistic on it. Now, I want to use that molarity in Part B when I have the tartaric acid trials. So with the tartaric acid, it was now a solid. So we're going to first use the molarity of the NaOH that we just found and the volume that you use in the tartaric acid trials and get a moles of NaOH. From moles of NaOH, we can relate that to the moles of tartaric acid. Now remember that tartaric acid is a diprotic acid, so it takes 2 NaOHs to react every 1 tartaric acid. So we'll make a coefficient ratio and figure out how many moles of tartaric acid were in that sample. Now remember, we weighed it out. So now we have a mass and we have a moles. Mass divided by moles gets us molar mass. So now we can calculate the molar mass experimentally for each of those 3 trials that you did of the tartaric acid. Once you have that, you can get an average, you can get a standard deviation, percent relative standard deviation. Then I want you to say, okay, but I can look up the chemical formula of tartaric acid and go find its molar mass from the periodic table and figure out what it really should have been. Once I have a known, this is what it really is, here's your experimental average, now you can compare them and do a percent error and see how close of a job did you do. Then we're going to go back, and now instead of taking just your 3 trials from the standardization runs, you're going to take the entire class's data of the standardization runs, and we're going to do some statistics on it. We really can't do the statistics with 3 trials. To do statistics, you really should have at least 5 trials. And honestly, statistics work better when we have like 10 or 11. So we'll talk about what to do. Let's kind of go through, again, those first calculations. All right, so the titration equation. So if I have 2 solutions, then I'm probably trying to find either the molarity or volume of, generally I'm looking for the molarity of one of them. So one of them I know the molarity, I know the volumes of both of them. How much did I add into the flask of one? How much did I add into the flask from the burette of the titrant of the other one? And then I have to know the concentration of one of them, and I can find the concentration of the other one. Note that I have to consider the coefficients. So I'd have to know what I'm reacting and have a balanced reaction. And then I can use this formula. And this formula is a one-shot and done. You can use milliliters as long as you use them on both sides. And this works out pretty good. So in this particular example, we were using HCl as our acid and NaOH as our base. And if I write out the reaction of HCl and NaOH, it's 1-to-1. 1 HCl reacts with 1 NaOH to make 1 NaCl and 1 water. So my coefficients are both 1s. So if I, for instance, use 50 milliliters of a solution and I knew it has HCl, but I don't know what its concentration is, and I add 28.39 milliliters of 2 molar exactly NaOH, I can now plug that in. So I'm looking for the molarity of the acid in this particular example, although in our example we're looking for the molarity of the NaOH. And then I solve it and I get my answer. So you're going to calculate the concentration of each of your 3 runs. You're also, when you do the class data, you're just using those volumes, you're going to use that same equation and calculate the molarity of every single run done by everybody in the class. But moving on with your data. So you have your concentration for the 3 trials, you average it. We're going to use that average concentration in part B. So your moles of titrant, in our case, we titrated NaOH with tartaric acid. So tartaric acid is our analyte, the solid. NaOH is the titrant, the base. And we know the molarity of the NaOH from what you just calculated. You use the average value. And then the volume would be what was the volume of NaOH added on that particular run. And then the moles is equal to the moles of NaOH that you just got times the coefficient. Now remember, it's 2 moles of NaOH per 1 mole of tartaric acid. So this is going to be 1:2 ratio. And then once I have moles of tartaric acid, so every time it says analyte, you're thinking tartaric acid. Every time it says titrant, you're thinking NaOH. Now I know the grams of tartaric acid. I know the moles of tartaric acid. I calculate a molar mass by dividing them. So you'll do this for all 3 tartaric acid trials. Once you do that, you can get an average. I'm asking you to calculate some things like standard deviation, percent relative standard deviation, and and part per thousand error. And on some of them, on the tartaric acid, we're going to do a percent error. So just to remember these formulas, I know you did them in 123. It's the deviation. First you get your average. So my average is, the deviation is the individual value minus the average. And I take that for each trial, I square it, I add them all up, I divide by n minus 1, because this is a sample. So this is a standard deviation of a sample. And this is how I get my answer. Also, we're using Google Sheets, and they have a function called standard deviation. Just be careful, there are 2 functions, standard deviation of a sample, standard deviation of a population. A population is every single possible value in the entire, so every single possible titration. We don't have that. You could titrate a million more times. So you have to make sure to use the standard deviation of a sample. But you now can just use the Google Sheets function. We made you do all the math in 123. Okay, once I have the standard deviation, the relative standard deviation is the standard deviation divide by the average and then multiply by 100 to get into percent. So it's pretty easy. I will use the percent relative error only if I know the true answer. So I can do this with the tartaric acid. Once we calculate the real molar mass, I could compare the average molar mass from the tartaric acid trials to the accepted value, which would be the molar mass that we look up from the periodic table. The other thing on the titration, I asked you to do part per thousand error. So in this case, the error would be the difference between the trial and the average times 1,000. So I'm using the average molarity of the NaOH, the class average, as being the accepted value. Actually, I think I said for the molar, for when you're doing part per thousand, use your average. So take your average value, subtract the molarity of that particular trial, multiply by 1,000, and then divide by the average molarity. This is kind of saying within your 3 trials, where were they? How close were they to the average? Were they all apart, very far apart, or were they all kind of close together? Again, I could, if I knew the actual molarity, I could use that instead of the average, but we don't really know. So I'm going to ask you then to look for those. Ideally, if you did good titrations, all of your part per thousand errors should be less than 5. That may or may not be true. And what is considered acceptable would be changing on the lab. So let's see what you can do with that. So that's just going to be your 3 values doing this on that. Then you've gotten all your data, you basically have done the lab, except now I want to do some statistics on a big sample size. So we have 12 people times 3 titrations. So we have 36 titrations that we did on the NaOH HCl. So we knew we all use the same HCl, we all use the same NaOH. So we now have basically 36 data points of the molarity of NaOH done by different people. And we can actually do some statistics. So I want to point out a couple vocabulary words. Q1 is called the first quartile. And the idea is that if I took all of the measurements and I sorted them, the one that's 1/4 in along the way of a sorted list would be the first quartile. The one that's 3/4 in along a sorted list is the third quartile. So the third quartile minus the first quartile is called the interquartile range. And then I have outliers, are basically these measurement values that are so far away from all the others that they're likely to be in error. So one way, and the way I'm going to have you test for outliers is, sometimes we're like, I don't think that's a good titration. But you can't just delete data because you don't like it. That's not how that works in science. So you have to have a legitimate reason, and one reason would be a statistical basis to say it's an outlier. It's so far away from all the others that something must have gone wrong, even though I don't know what went wrong. Of course, if you overshot the endpoint or something spilled, you could say, I know that data is no good because I have specific reason. But otherwise, just looking at a number and saying it's way off is not sufficient. So one method we can use is that you can say that if a value is 1.5 times outside the interquartile range, that's so far away that we'll call it a outlier. So what that means is that the lower outlier boundary is the first quartile minus 1.5 times. So we have our first quartile, our third quartile, our interquartile range. I take 1.5 times that range. So 1.5, way out here, that's the lower outlier boundary. And then I have a higher one. So if this is the difference between them, I'm going to go that much and a half. Anything past that is considered an outlier. So Q3 plus 1.5 IQR. Okay, it's easier said than done. Let's kind of do it with an example of data. You're going to use the data of the, let's see if I can't make this big. Here we go. All right, so I have this list of data. It's just a list of numbers. Your numbers would be the molarities that you calculate for everybody's titration data, which will be added to your Google Sheets on the Thursday night. So this is a list. Now the first thing I do, I need to sort it. So I'm going to take my list and I'm going to copy and I'm going to paste it. But I want to make sure, if you have using formulas in here, make sure you use this paste special and paste values only. Now there's nothing special. This is not a formula. It's just a type number, so it wouldn't make any difference. But if you had a calculation in there calculating the molarity, that would be an issue. So now I can select it, and I'm going to use this data sort range. So data sort range. Now because I didn't select the title where it says sort, it doesn't have a header row. But if I had done the whole column and I included the words part, I could put a header row on it. So since I don't have one, I'm going to say sort it by column C. So note, now I have it going from lowest to highest. Statistically, usually they go from highest to lowest, but this works great. I also kind of want to put which one each one is. So I'm going to put it in order. So this would be the first one, this would be the second one. Quick hint, after I have 2 in a row, if I select them and then I see the little box here, if I put it on the box and get this and I click and drag down, it'll fill it in. Okay, so this is like the index, like this is the first one, this is the second one, this is the third one, and I can see this. So now I have a set of data that's sorted. I need to figure out which values on my first quartile, my third quartile, and I may as well figure out the median, which is essentially it's the second quartile, it's halfway in the middle. So I can see from my index, the last one is number 17. So N is how many samples I have. I have 17. I want to figure out the index by taking 17 and dividing it with the 1/4 and the 3/4 of 17. So I'm going to take equals 17 divide by 4. So it's 4.5. And this is equals 17 divided by 2, or 2/4, equals 3 times 17 divided by 4. So 3/4 of 17. So notice it tells me which value will be my Q1 and my Q2 and my Q3. So for my Q1, it says 4.25. Well, I don't have a 4.25 value. I have a 4 value and I have a 5 value. So I'm going to go average between these two values. Now, when I look at 4 and 5, they're both 13. So I don't really even need to take an average. It's like, since they're both 13, anywhere in between would also be 13. So that's going to be 13. Let's look at Q2 is 8.5. Well, here's 8, here's 9. So 8.5 would be between 15 and 15. Since they're the same, that's 15. Q3 is at 12.75. So here's 12, here's 13. It's between 12 and 13. Well, I have 18 and 19. Fancy statistics you'd have to interpolate. We're close enough to say I'm just going to average in between 18 and 19. So I'm going to say equals 18 plus 19 divide by 2. Now you probably could do that in your head and say 18.5, but if they weren't like really clear what they were, so you average it. So that's my Q1 and my Q3. I'm basically finding those places along the list. My interquartile range is then Q3 minus Q1. So just follow the formula. Equals Q3 minus Q1. Done. I don't want to do autofill. 1.5 times. Remember, my outlier is 1.5 times the quartile range past Q1 and Q3. So first I want to do what is 1.5. For 1.5 times this 5.5, 8.25. Now I want to find the lower outlier boundary and the upper outlier boundary. So I subtract 1.5 of that from Q1 and I add it to Q3. So Q1 is 13 minus 8.25, 4.75. And this one equals Q3 plus 1.5 times the interquartile range. So it says 4.75 and 26.45, or 7.675. So those are the numbers I'm going to use to pick outliers. So I'm just going to sort of draw like a line in some sense. So 4.75. So all of these between 4.75 and 26.75, so these are all not outliers. Anything that's below 4.75 is an outlier. So I'm going to highlight this. This is an outlier. And 29 is above 26.75, so it's also an outlier. Now, I'm going to just, we can just kind of do a frequency plot of these. I think we can do a frequency plot. Just normally we would show a chart, like you can see what we're sort of talking about, except, let's see. This is showing them all, but I want to do like a frequency chart. I don't know if I can do a frequency chart. Nope. Guess you can't do that one. In order to do this, I'd have to make a frequency chart. So let's do this. 3, 4, 5, 6, 7, and I want to go up to 29. And I'm just going to say how many I have of each one. So of 3, I have 1. To do this real quick. 8, 9, 13, 13. So 8, 9, oops. Yeah. Nope, sorry, 0, 0, 0. So 8, I have one of those. 9, I have one of those. I have 2 13s, 2 14s, 2 15s, 1 16, 1 17, 1 18, 2 19s, a 21, 24, and a 29. I think I can do this. Let's do, even though we never do these charts, this time I'm gonna do a bar chart. So this is kind of looking at our distribution, right? These are all these numbers we measured, and this is how many of them I have, whether I have one or two of them. And I can kind of see what's going on here. The idea is that this is a distribution. Most of the values are in the middle, right? That's what I would, it looks a little bit bell curve, not really. But see how these are way out? This 3 and this 29 are kind of way outside the gather. Remember we said that 13 was the first quartile, and I think 18.75 was the third quartile. So this is where most of the data is. This is now 1.5 outside of that, and this is 1.5 outside of that. So that's what we're really trying to do. I'm showing you graphically what we're trying to do. You don't have to make a graph. All you have to do is do this part. So you're going to sort your numbers. You're going to find the outliers as ones that are lower than the lower boundary or higher than the higher boundary and highlight them. Those would be ones that we would statistically take out, and then we would only average all the others and then get that average. From there we could get a standard deviation. And now that you have the average of the classes, you can kind of compare the class's average with way more data points to your average and see how good of a job did you do compared to the class. So that's what I want you to do for the statistics. Hopefully that's clear. I will see you in class. Bye-bye.